Okay, so here we go. Wow. Here we are. So the deal is, I don't actually know. I'm just kind of messing around with some things. I didn't want to wait too much time to program something. Just want to do something. Yeah, that's pretty much it. I'll take a look at a Leetcode problem today, get some practice. I don't really like waiting too much time, putting too much time in between working on things. So I moved the camera. I had the camera, I couldn't really, well, I'm not really sure where I want to put the camera, but I have a chair here, so I figured, okay, well, I could just put the camera on the chair, and it's like you're kind of just watching me from the side, I suppose. Things that were like from the front were a little awkward. So you notice I'm not wearing my glasses. I'm trying to do a kind of holistic healing kind of approach deal thing with my eyes where I don't wear my glasses, and so it gives me some practice looking at things without my glasses on. And in theory, my eyes will kind of slowly over time adjust themselves to kind of improve my vision. That's the theory. I don't know what's actually going to happen. Kind of approaching it the way you might approach like physical therapy. If you can imagine someone who's like paralyzed, they want to slowly use their muscles, and over time it gets stronger and stronger. That's what I would like to do. What's actually going to happen, I have no idea. My eyes might never improve. For those of you who don't know, I'm basically blind. I can see about here, and after that everything's blurry. And it's been like that since I was a little kid. But I distinctly recall when I was much younger, I didn't wear glasses for a long time at a summer camp type of thing, and my vision improved dramatically during that period of time. I remembered that. I'll never forget that. And I never really had the opportunity, or never felt right to like try to do that again, where I don't wear my glasses and just kind of have my vision as it is, and just kind of let it sort of I guess let my muscles kind of adjust on their own, because I can kind of squint a bit and see, it's like it is very much like a muscle thing, it's like it just needs to be slightly, everything just needs to be slightly, moved, I guess. So I don't know what'll happen exactly. I'm kind of interested to find out if I don't use my glasses that much for a year or two, if there's any improvement. It would be interesting to see, interesting to know. But anyway, so this video is not about my glasses or my eyes. It's all about my programming skills. It's important to practice, and I've solved hundreds of problems now online, thousands actually at this point, thousands of problems. I don't know thousands. I know over 1,000. I don't know if I've hit 2,000 yet, but I've solved a lot, and I don't know. I think it's good to just kind of keep my skills sharp, keep practicing. The thing is that the problems get easier and easier as you go over the years, over time, and I've noticed that. I have improved so much so that like problems start becoming kind of routine. They start becoming kind of well practiced, kind of recognizable, and it's kind of easy to go one thing to the next. There will be a point, I think, where I'm kind of just banging out these problems like within 15 minutes, see the problem, understand it, solve it, get on to the next thing. And these are the kinds of problems that interviewers like to ask, so it's useful to practice this stuff. Although I don't know what's going to happen, but there's a good chance I may never actually need to interview again. I don't know. It's good to have this in the back pocket, though, in case I want to, in case I need to, or have the desire to, something like that. I don't know. I get a lot of attention now from employers, way more than I could even keep track of. That's great. I mean, that's fine. I'm grateful for that. But I get tons and tons of stuff from recruiters and employers and folks looking for someone to help them with something, and it's good. Makes you feel wanted. Always have opportunities. Always have sort of a place to go if I need a job. The problem that I have though with a lot of these places is like the reasons that I would have to leave my job probably would be present at those jobs too. Like the things that bother me, and the things that are negative that I would want to be avoiding, are probably just there at the other job too. So, so it's kind of like I don't know. What should I do? I don't know. I'm very conflicted about it all. I have been seriously considering finding another job though recently. I've been like, I might start doing that. But anyway, I definitely want to practice my skills before I start doing any of that though. So, and I probably should just be doing this regularly anyway. So anyway, let's. So you'll see me leaning forward quite a bit to see, because I don't have my glasses on. Effectively blind as a bat. But here we are. Let me see something quickly. Yeah. Effectively blind as a bat. That's in. Oh, is that the right one? Yeah. Okay. Yeah. Today, let me also make this bigger so you guys can see it. As you see, this is the medium problems on Leetcode, and I've solved, a few hundred of them now. Let's see, one. I like doing this, man. I just like seeing all the check marks. Makes me feel good. But yeah, we're on this one here. Different ways to add parentheses. That's 241, or number 241. It's not. I didn't solve 241 of these. I think I've solved a couple hundred, but not too many mediums. So let's read that problem. Different ways to add parentheses. Given a string of numbers and operators, return all possible results from computing all the different possible ways to group numbers and operators. The valid operators are plus, minus, and multiply. So input 2 minus minus, minus 1 minus 1, 0, 2. Output 0, 2. Explanation. 2 minus 1 is 0. 2 minus 1 minus 1 is 2. 2 times 3 minus 4 times 5. Negative 34, negative 14, negative 10, negative 10, 10. So, oh, I see. So there's a lot of different ways you can compute these. That's a really interesting question. I've actually solved this before, believe it or not. I've solved a variant of this. It's a string that you get. Okay. So, yeah, we'll sit down and think about it. So this is a pretty interesting question. Yeah, I've actually solved this problem before in a way. The question was, it was similar. It had division in it, not just addition, subtraction, multiplication. And it was also, I forgot what the numbers were, but you had to operate on these 4 numbers to try to get a certain other number. And I was like, I don't think you can. So I wrote a program that sort of brute forces all the way through it. And I was right, you can't. There's no way with those operators. You had to invoke some other operators in order to go through it. The way I solved that, though, was probably not the way that I want to solve this. I mean, maybe, I don't know. I did a backtracking algorithm, I think. What did I do? I actually used, it's actually not the same question here. It's not actually the same question as here. That question is slightly different. So I take it back. I didn't solve this one. I solved a variant of this. That's not really the same question. It's not really, I wouldn't even call it a variant, just a different question, where you could move and interchange your operators however you wished and move your numbers however you wished. Here you actually can't. The operators are set and the numbers are set. However, what's not set is the order of those operations, which is not quite the same thing as the other question, which was sort of you could manipulate your operators or your numbers however you needed to in order to achieve the result you're looking for. So different questions. This one, I believe, I want to say you can solve it in a similar way. I want to say like a depth first search probably is the way to go, where you basically select the first operator you select, I guess, a pair of parentheses, or just you select the first operator to compute, the operator and the pair of numbers to compute. And then once you do that, that puts you in a certain state. And then you have, and so obviously like the first sort of loop you would be able to select from from left to right, sort of any of the operators, and then obviously each of those operators you would get a certain pair, and that would change the state, and you would operate again, with a similar loop where you select the next pair. And what I'm wondering is, there's a couple things that are tricky about this. So I think that's a reasonable solution, right? And obviously the backtracking part of it was that when you finish, recursing, you would undo the things that you did, and then obviously complete the rest of the loop. That should work. The base case is obviously when there are no more operators left, you just have a number, and you would just put that into a sort of a global return variable, I guess. You do it that way. Sort of static. We'll call it static. I don't know what the right word is. Static with regard to the function. Something like that. In this case, I'll probably write the function as like a lambda sort of routine. And that'll just be a variable that's scoped, it's contained in the scope. So tricky things about this would be, you don't necessarily want to maintain the state as a string. You want to parse the string into something representing the state that's kind of efficient to manipulate. And the thing that's kind of awkward about this is that there is a notion of like an ordering. In other words, the numbers and the operators, like the order kind of matters. But you also want to be able to sort of remove an operator and two numbers from whatever data structure you use and replace it with just a number. You kind of want to do that efficiently, and you kind of want to put the number is going to have a sort of a notion of a position. So that's a little awkward, like manipulating the state, like moving to one state and then moving back to this from that state is a little bit of a tricky thing that I think we should think about before we try to implement this. But yeah, I think just a basic depth first search should solve this pretty quickly. Should be relatively easy. Let me see. How can we... The thing that's awkward is the state. Yeah, how are we maintaining the state? Because it's actually, there's nothing wrong with, like, we don't need to use like a we don't necessarily need to use like a persistent data structure or something that would emulate like a persistent data structure where, like, we don't, like, in other words, you could have like your list of operators and your list of numbers, and then when an operation is consumed, you would copy the list of operators and copy the list of numbers, and then change that accordingly what you've copied, the result, and then and then the recursion would sort of operate on that, right? In theory, you could do that, and then obviously after the recursion, you would return back to what it was. That's sort of like a persistent version of it, where you sort of have like a stack of the data structures, and you kind of like return back to the previous state. But you'd be copying the state each time. That's sort of the persistent part, is that at each step you sort of have a full copy of the data structure, the whole data set, and that's sort of how you move from state to state. It's not necessary to do that. with depth first search algorithms. Like you often can return to the previous state without copying the whole state, if that makes sense. So you basically just undo the differences that you make. You just have to store the differences instead of rather than the whole data set, which is kind of interesting actually now that I articulated it that way. But which is just a lot less memory, is I guess what I'm getting at. A lot less effort, a lot less memory. But I'm actually not sure how to do this with this particular data structure because it's kind of awkward. It's just like if we just had a list of numbers left to right, when you remove two of the numbers and replace that position with another number after the operation consumes the numbers, and then same thing, remove that operator. It's relatively so it's not too bad to do that in an array, we'll say, like a vector, because you can move the value to the end, and no, actually it doesn't really work. Actually, no, because you still have to move everything down, so it's really awkward. It's I don't know, man. One approach that may be possible would be to sort of turn this into like a tree type of structure, I guess. I don't know. It doesn't seem right. No, that doesn't seem right either. I'm just thinking, how can we do this? A little bit stumped here. I don't know if it's the data structure I should be focusing on. I'm wondering if it's there's got to be a way to do this. It's not. So what's kind of interesting about this question is it's sort of special because it doesn't necessarily lend itself easily to any particular data structure, because the data as you're given, each operator operates on a left and a right number. So each number has a relationship to excuse me, 0, 1, or 2 operators. Obviously, if the number is alone, it has no operators, but if there's 2 numbers and there's an operator between them, each one is sort of connected to 1 operator, but each number could be connected to 2 operators, or most of the numbers could be connected to actually 2 operators. And so there's this kind of I want to say you could use a kind of graph structure to remove nodes and reassign the relationships, where you'd have nodes for the numbers and nodes for the operators, and you'd have links between like a linked list, I guess. Maybe a linked list would be the way to do it, actually, thinking about it now. Maybe that's what I need. Interesting. Would a linked list do the trick? Would that be what I want? Sort of a special linked list, and you would update yeah, you'd remove like 3 nodes in the linked list. Each time you have an operator, you use an operator, you'd remove those and replace that spot with the result, and then you would operate, you'd recurse, and when you went backwards, you'd put those nodes back. Actually, you'd actually put the nodes back. Is that any is that any better? I don't know. You have this really tricky thing that you need to do, where at the end of your recursion, you would need to give back a pointer to the right point in the linked list where you put back the 3 nodes that you removed. That's pretty interesting. Obviously, they don't have to be the same nodes. You could just create new nodes and put them back. Yeah. In theory, you could do that, right? You could have part of your recursion is that you would actually return you probably want a sentinel node of some kind, sentinel nodes, in order to easily add and remove nodes. Yeah, you really don't need a tail. You just need a sentinel head. So you could always remove and add nodes easily. But you basically, in your return value, you want to say, okay, this is the node that you're going to put. That's super interesting, man. It's kind of, excuse me. Yeah, actually using a linked list is really interesting. So, you remove these 3 nodes, you put a new node there, you would recurse. Somehow though, after the recursion, that new node that you put, you want to actually remove that and put back the 3 nodes that you. And now the problem with that is that after the recursion, you need to somehow know basically have this node position, because the thing is, in theory, the recursion, this linked list is going to get manipulated all over the place, and the position that you want to manipulate is basically going to be lost. Like you won't be able to you can't use a pointer to a particular node and say, okay, that's the node that we're going to put back the 3 nodes that we removed. Right? You're going to remove 3 nodes and put one there, and then you're going to reverse that. You're going to remove that 1 node and put 3 back, and do that over and over again. Right? But the thing is, like, it would be a lot easier to just like copy the linked list. The problem with that though is I think it's way too much extra work to do that. I think it's a lot of extra work at each step, at each level. Unnecessary amount of extra work. Really a lot of unnecessary extra work. So I want to say something like you can do. You need to return at the end of it's really the base case is the only time you actually return anything. You need to return the position that you're going to where that node was placed, the node right before it, somehow point to that node. That way you can remove that node and add the other three nodes back, or 3 copies of those nodes of what was the data in those nodes. Recreate those 3 nodes in the list. The problem with that, though, is that's going to be part of what's returned. Yeah, the problem with that, though, is that how do you do that? How do you achieve that? Like, how do you? Because you're at each iteration, you're just going to dig deeper into the linked list, right? You're going to just be destroying the linked list the whole way down until you get to a base case, in which case it's just the sentinel node, the head node you would return, and that should be fine, because then you can remove that node and add the 3 nodes that you had right there. That should work. It's just you're going to fall through your iteration and return. There's sort of another base case at the bottom, and right. So I'm just thinking, like, I don't know if you did, like, I have to go through an example, I think, to really think it through. So like 2 minus 1 minus 1, right? 2 minus 1 minus 1. If that linked list of each character, 2 minus 1 would become 1 in your loop. You would iterate again. That 1 minus 1 will become 0 in your loop, and you would iterate again, and then there you hit a base case, and you'd go back. Now your return, you have the sentinel node. You say, okay, you want to put it was 1 minus 1 is what you removed. Now you're going to remove the node 1 coming after the head, and you're going to replace it with 1 minus 1. Oh, excuse me, node 0, and replace it with 1 minus 1. Okay, and then you actually fall through that loop. That there's like a for loop where you're iterating over all the possible through the linked list, I guess, through each linked list, through each operator, really is what it would be. So yeah, that for loop would exit. Oh, that's interesting. Yeah, because you kind of, it's an interesting thing. You kind of you add these new nodes back, and then you actually iterate past them, and then you know, sort of on the linked list, and then sort of recurse on that. It's kind of interesting how this looping is going to be put together. But so yeah, you remove 0, add 1 minus 1 back, and then there's nowhere to loop after that. So you just return there, and then what do you return there? I guess it would be, you would have to know which of those nodes that you manipulated, right? Because you had 2 minus 1 to give you that 1. That first node is actually the node that you want to return. I don't know if I don't think it's the head node every time. I don't think it's the sentinel node every time. That doesn't make a lot of sense to me. But in this case, it happens to be, I don't know what exactly you would return there, but then you return and you say, okay, now we've got to take the 1 in the linked list and replace that, remove that, and in its place put the other 3 nodes, which was the 2 minus 1, and then move our operator to the minus 1. right, pass those three to the next operator and recurse, and then now we have, you know, that when not recurse, but yeah, we move it to that operator, and we iterate it. The next sort of part of that loop would be 1 minus 1 is 0, so we have 2 minus 0 now is what we kind of iterate on the recursion. Which again would go down to 2, and then would come back up to 2 minus 0, and then come back up. Now, okay, yeah, so when you come back up again, right, so 2 minus 0, when you come back up again, it's not the head node. You don't replace 2 with 2 minus 1. It's actually the 0. It's the... What I think is interesting is maybe you can't do it this way. I don't know. I'm super uncertain, super confused. Like I said, at each step you would be manipulating so much of the linked list that it would be difficult to know which node you need to change. I want to say something like from left to right, you'll always be able to, because you're moving from left to right at each step, you'll always be able to access the node that you need to. In other words, that node won't disappear. Like maybe I can make that assertion with this sort of approach, this algorithm, that, so like for instance, the head node is going to be there when we go, 2 minus 1 minus 1, we go down to 0, the head node will be the right node to come back up. Well, that'll always be true for the bottom level. It'll always be one operator and two values left and right, but one of those two values, when you go back up the next level, is going to be the one that you need to manipulate. And where basically you reverse and you remove that node and add 3 nodes back. So for like 2 minus 1 minus 1, you do 1 minus 1 gives you 0. You have 2 minus 0. Remove those 3 nodes, add the 0, go down to the next level, remove 2 minus 0, add 2, hit the base case, go back up, remove 2, add back 2 minus 0 to the head, and then now you need to somehow know that it's actually the 0 node, the minus, not the head. You don't want to touch the sentinel node. Now you want to touch it's actually the node where it has a negative a minus character, a subtraction character, a dash character. That is you know what you can do in these situations is the fall through character, the fall through at the bottom, you can keep track of what characters you just added, the operator that you just added. You need to know if it's the left or the right, though. That's the thing. So like when you get down to like 1 minus or 2 minus 0, you need to know if it's the 0 or the 2. It could be either the head node or the subtraction operator. But basically, the 3 numbers that you add, the 3 nodes that you add back, one of those is the one that is manipulated next. Now that may not be the case. That may not necessarily be true. No, that's definitely not always true. I don't actually know. I don't know. I don't know. No? just want to return to the state that you were in before, but how do you do that properly? You could, like I said, you could return a value or return a pointer to the right node that you need to add these 3 nodes back to. Remove the node that you just added, remove that and add these 3 back. However, that's simple enough, but the next iteration, for instance, like 2 minus 0, which node do you remove there and add back 3 nodes? You remove the 2 and add back, you know, it was 1 minus 1, I think. Or do you remove 0 and add back 1 minus 1? And how do you know which one? That's really tricky. That's actually really tricky. Obviously, it's a lot easier to just copy the linked list every time and just point back to the previous linked list. But the reason why I don't want to do that is it's expensive in terms of memory and the algorithm itself. Or it takes a lot of extra time to do that, a considerable amount. Too much, way too much. So, well, for this problem, it may not be too much, but in theory, you can avoid that and should try to avoid that. But the question is, how exactly do we do that? And we don't want to loop from left to right across the linked list to figure out the answer to that question either. We want to do it in constant time if we can, constant time. Because if we do it left to right, then we might as well just copy the whole thing every time anyway. Because it's going to cost us, it's just a constant factor more, constant multiple, which would be asymptotically somewhat negligible. Not negligible, but we can somewhat ignore it. So, because it could be the case that it could be like in theory you should be able to kind of jump back from each state without having any knowledge of like the previous states that you jumped to or from, something like that, if that makes any sense. The reason for this is you could like if you had a much long so you could have like a much longer example where changes in one spot don't affect, like in other words, you could split, you could have a much larger example and split on one operator in the middle and have the left side and the right side, and you do all kinds of stuff on the left side, all kinds of stuff on the right side, but they don't know anything about each other until they meet on that one operator, I guess. I don't know what I'm saying here. I don't know what I'm trying to say. I want to say that there's like a way to break this if we... I don't know. I don't even know. I don't even know. So, simply keeping a pointer to the position of where a node was added isn't going to be enough, because that pointer is going to get that node is going to disappear and be replaced with another node in the recursions and as you dig deeper. When you come back though, the state should be the same, except it's going to be a different node at that position that now here's something really funky you might be able to do. Actually, you want to really not get fancy, but keep kind of get a little bit out there. I have an idea, actually. Don't delete these nodes when you remove them. Just move them somewhere else where they're still in memory, but they're out of the way. In fact, every node that you create, don't delete it. Just move it away into maybe a hash map, we'll call it, into a hash set. Let's do it that way. Yeah, actually, that's a lot better. That's a much better idea. So these linked list nodes, they don't get deleted. They get put into a hash set, an unordered set. Excuse me. I want to say an unordered map of some kind, a hash map, where you know which combination of nodes you use to create that node, and that's basically the identifying tag. And so what you can do is you actually can keep a pointer to those nodes. So when you add and remove nodes, and when you create nodes, you can put them into this map. And what will happen, in theory, is that then when you put these nodes back, you will actually have the pointer. You actually won't destroy the nodes that you need to use. You can actually maintain a pointer. And obviously the hash map wouldn't even be the nodes themselves, but just the pointers to these nodes. You can store everything in locally. Yeah, locally should be fine. Actually, in the hash map, you do want the node to be stored, because a pointer to the node so the hash map would be local to the function, static to the function, but it wouldn't be. Yeah, you don't actually want the nodes to be, if they're like, if you create them locally only, then you don't store them in this hash map, then they get destroyed when the function ends. And yeah, something like that. Yeah, you want them to be dynamically allocated, somehow dynamically allocated. I think when they're put into the hash map, their scope, they maintain their scope. I want to say something like that. It's getting really complicated. It's getting really complicated, but I think it's the right way to do it. It's a pretty interesting question. I'm glad we looked at it. Definitely stretches your mind a bit here. Definitely stretches your mind a bit. But yeah, depth first search is the way to go. Obviously, we could have solved this a while ago if we just did like a copy of the state. I think linked lists are good. So you can easily remove nodes and replace a new node at that position. The tricky thing here, though, I think, is we want to, well, for starters, actually just removing stuff from linked lists is kind of awkward. And removing and adding things from linked lists it's always awkward, but shouldn't be too bad. But we want to, each node, we want to actually save those nodes in a hash map So the 3 nodes that you remove, I mean, you can do something kind of funky where you have like a sentinel node that just stores the 3 nodes that you removed, and then you have a pointer to the node from which you removed them. That's where, and that gets saved on the stack, and that node doesn't get destroyed or anything. It just stays there, and that should be restored when you sort of, after all of your recursions. That node should actually just be in the same spot that it was in, and then you can take those 3 nodes off of that other linked list, put it, remove. So there's another node that gets created that you add to that other node, I guess, and then you recurse, and then you say, okay, we're now going to remove that one and put back the other 3, and move our operator pointer. That's pretty funky. That's pretty interesting. It's kind of weird. Yeah, it'll be stored on a temporary linked list on a stack. And there'll be this node that's added. And it's created and added to the list. And then, yeah, it's super interesting. So those 3 nodes never get deleted. Neither, by the way, does the node that gets created. That doesn't get deleted either. Created and added, and then later it gets removed, and the other 3 get placed onto it. When that is removed, I think actually when that's removed, I think you can just destroy it at that point. I don't think you need it anymore, truth be told. Actually, I don't know. That's a good question. Do you destroy that node or not? That's kind of a hard question to answer. I don't know. I don't want to find out the hard way because there's already so many things I'm not sure about with this approach. I wouldn't know. I wouldn't be able to figure it out. I would be like, wait a minute, why isn't it working? Oh, it's that thing, right? Those 3 nodes never get deleted. You add a node in there, but you do remove them, put them on a new list. That list is on a stack. You go recurse, and then when you finish your recursion, you start returning. I really do think that node can be thrown out altogether. The one that you created and put in the, after you're done with it, after you replace it with the other nodes, going back up the stack. Yeah, I do believe you can actually just remove that. And the reason why is it's like a tree. It's once you traverse back up the tree from that point, you're never going to return to that point again. Or if you do, you just it creates a new node altogether. Like it just generates another one at that point. I want to say because of the tree nature, it's not necessary to maintain that. You just have to be able to go back up. That's all you really care about. You don't care about being able to go back down again. You're not going to go back down that path again. Yeah, that's actually what it means to come back up from that path, is that you're going to go down another path now. So, am I right about that? Oh. I want to say I'm right about that, but it's like, careful. Careful. Yeah, that node to remove, once it's ready to remove it, because it's, yeah, because you generated it, it should be at that point beyond its use. So you can just delete it. Yeah, it's fine. Interesting. Don't need to save that anywhere. Pretty neat. Then you would insert those 3 nodes back at whatever that pointer was. And yeah, because you're not deleting any of the nodes, it shouldn't be an issue. Huh. Really interesting. So actually, it's not really I probably want actually most of the operations to be abstracted away in the linked list. You want like a stitch kind of a command, because actually that's what you're going to do. You're going to stitch back this linked list, stitch to a certain node, stitch to a linked list. You're going to stitch. Huh. Stitch either a node into a spot in the linked list, or stitch a linked list into another linked list, into a spot in another linked list. And you're going to update your linked list with the head and the tail, the new head and the new tail. Interesting, really interesting. Huh. Wow, I don't know, man. Linked lists are so funky. It takes such a long, like, takes me a very long time to kind of think through the operations with linked lists. But I think a simple stitch command is super useful. So I'll probably write like a linked list data structure, and then have like a character, yeah, for each node, and then we're going to operate on the linked list in sort of groups, I guess, and then we'll have another linked list. We have sentinel head nodes, and we'll have like a stitch, a head and tail pointers, and a stitch command. And we could stitch one linked list to another linked list, A to B, and we would say, or no, it's the stitch command would be overloaded, so there'd be 2 signatures. One would be the list that you're stitching into, a pointer to the node in that list that you're stitching into, and then a pointer to you really could just do two pointers to linked list nodes, and the thing is, I really want to have sentinels for these linked list data structures. I really like the idea of operating on a linked list data structure. It's not just, well, actually it doesn't really matter. I mean, the sentinel head node is like, meh. I like having like a containing linked list data structure, and then like a linked list node, instead of just like, because you could just do like just the linked list node, and then obviously if it's a head node, then you know, like you could just operate on keep linked lists really simple if you wanted to. But I like having kind of a linked list with like a containing data structure that has like a head and a tail pointer, which is kind of another decision to think about. Like, I think for most applications, you really don't need that, the head and the tail. It's like not really necessary. You can kind of keep that, kind of know that from the context, I guess, if that makes sense. I think you're better off just having like a node class and keep it really simple. And the stitch could be actually like a helper function. It just has two nodes. You stitch one node to another, and then basically assume that the second node, the second pointer that's given as a the second pointer that's given as a parameter, assume that that's a head node. Yeah, you would end up merging. You could actually merge two linked lists because it's not impossible for two linked lists to actually connect to each other, right? You could have two linked lists, and they sort of, these two nodes point to one node, and that one node is another linked list. You could have that situation. I guess we just won't account for that situation. That's kind of why I'm thinking about, like, I want to have a head and a tail and keep things in a data structure and all that, and like kind of quote unquote keep things clean, you know, if that makes sense. So you run into some really funky errors if you start merging linked lists without realizing it. That's like Git repositories technically can do something like that, which is very funky. When you have to yeah, Git works totally differently, but Git has a similar kind of thing going on with Git differences. I feel like I should just start coding this, you know? I feel like I sort of spent a lot of time thinking about it. The solution itself is really straightforward, though. It's a backtracking algorithm, a depth first search. Yeah, we'll use a depth first search, and we're going to, you know, you have a certain state, change the state, recurse, and then return back to the previous state after recursion. You have a loop that kind of loops over. We're going to loop over. The state changes are going to be the operators, and we're going to have a linked list that'll kind of maintain the state. And you replace, you'll have three nodes. You're going to remove them, throw them into another linked list, and those are going to be, they're going to generate a new node that'll be replace those three. The three nodes are going to be an operator and two numbers, to the left and to the right. Now, something that's kind of a problem here is it's not necessarily a character. I didn't even think about that, but it's actually, in this case, it looks like all the characters are just each integer is a single character, each value, but actually these could be really you should make it a string, each sort of datum in the node, and you would then interpret that string as either an integer or an operator. Yeah, so we just need a small routine to figure out whether that string, and then convert that, you know, convert the use of that to an integer. Yeah, that's kind of a tricky thing. Right. Yeah, I mean, I think that's fine. That should be fine. The one through one pass of parsing, we get these strings. I just think you could have a Boolean that tells you you could do it slightly differently, and you could say, like, have a Boolean value that tells you whether or not it's in the node, that whether or not it's an operator, and then, you know, have a character if it's an operator, and if it's not a character, you have an integer. Technically, you can you can convert your integer to a character, I guess, and vice versa, character to integer. So you could just make these all integers, and you'll be able to store your integers as well as your operators, your characters. You just interpret the integer as a character. Actually, that should be fine. That should be okay. Unless these are like a gigantic integer, big integers that they throw in here, but I don't think they're going to do that. We could probably check to see what the inputs are. Yeah, hopefully the values you get aren't gigantic numbers and operators. Yeah, so actually you could we'll use longs just in case. So you could do relatively large integers, 64-bit integers. But yeah, the nodes could just be longs, and then you just interpret the long as a character and have a boolean that'll tell you whether or not it's an operator or not. So boolean and integer should be fine. Or boolean and a long. Just have to parse correctly. So you parse correctly. You have these linkless nodes. We'll keep it kind of simple. The node class. I'll make it an inner class just for this heck of it. The stitch operator will get 2 pointers to 2 nodes, and it'll be as simple as really you just point A to B. I mean, that's really it. Stitched, done. That's it. That's it. So actually it's super simple then if we just have simple nodes. Keep things really rudimentary. You'll have our sentinel node. Take these 3 nodes. Stick them on the sentinel node. And then take the node just before those. Put a new node in between whatever that last third node was pointing to. So I guess we'll do it manually. We'll do this kind of like removing these 3 nodes and replacing them with a single node. I guess you could abstract that away as a stitch routine, but you could do it manually too. I mean, it's simple enough to do it just one shot manually. And then you recurse on the state. Yeah, your recursion is actually going to start from the very beginning. There's a pointer to the very beginning. This base case. Got these nodes, operators. It's kind of complicated actually. Once you gather all the pieces together. I hope it works. I don't know, man. It's kind of a lot in one shot. I think we'll probably code it and then go to bed. Code it, run it, test it, go to bed. Yeah, relatively considerable number of pieces involved. Okay. So let's try it then. Let's try the parsing part. Let's do that. So let's create the node class, and then I don't know if we want to do this character by character. I don't actually know how we want to parse it. I would normally use regular expressions to do parsing, but I kind of want to try this without using regular expressions and sort of do a C-style parsing, kind of a C-style string manipulation sort of thing. Yeah, that's fine. So we'll start a parse subroutine, and you can build your integer as you go. You would, yeah, as you see each digit, you would multiply what you have by 10 and then add the next digit. And if it's not a digit, then it's an operator. And so you can finish you create your, take that integer you've got, create a node out of it, and that's your first node. And obviously have a sentinel node, and then you can start working on the next node. So it's should be pretty straightforward. So let me see. All right, let's start with that node class. Let me get an inner node class. Oops. Node, and we'll just say long val bool is up. We also want next, node pointer next. Oops. And we don't really need a constructor, quite frankly. Well, yeah, actually we'll create a constructor. Simple constructor. So it'll be long val bool is up. Oops. Yeah, bool is up. And the last thing is, and these are private. This is public. Publici. This is next, and literally just, I think we just do it that way, right? Val is up, and next, something like this. And I don't know, do I want to do it that way? I guess that's fine. I don't know if it matters. And we probably want, I almost want to make this public. Yeah, because it's just easier to manipulate it that way. But we can do something like this, just void, just a set next, which is node n, and we'll just say next equals n. Something like this, something simple, right? You can use it, yeah, just update. We don't really necessarily need a getter, do we? We might want to use getters. Simple setter. Really don't have to change either of these. We do need getters though. Yeah, so we'll just do. Yeah, okay. Get val. We don't really, I mean, yeah, okay. We don't really need this, do we? These getters and setters. I'm gonna do it anyway, but really don't need these things. I don't know. I'll do it this way. I'm not sure. Not super confident about this. We really don't need much. We probably could just get away without using getters and setters and just make these public. Not even make these private. And okay, so that should handle the node class. Oh, my back. Oh. Wow. You gotta remember to use your, squat instead of bending over. So right, the parsing routine is what we want to see. So yeah, let's do that. Let's do a parse routine. Auto parse something like this, and what we want to return is actually a node, and yeah, that's going to be the head node. So we start off with node pointer. It's really just node ret equals node sentinel. And value will make 0, is op false, and next is null pointer, and we'll call it sentinel. Oops, I don't know what that is. Sentinel. Alright. Now for the parsing, we're going to take a string, input, and we'll just say s, and we're going to say for int I equals 0. Yeah, okay, that should be fine. Si is less than s dot size. Oops. Character c equals s of I. Okay, so we do these things, and what we want to do is a simple check. It's we can do operators too. We can do a simple thing here. We say unordered set characters. Spell properly. Leetcode. I want unordered set. Okay, we spelled that one right. I don't know if I could do this initialization list here, but we want ops. We have 3 characters, right? Plus, minus, that's equals, and multiplication. Right? 3 different operators. We actually want to do something else too, which is an unordered map of lambdas, which is something kind of useful here. I'll show you that in a moment. If I can spell include properly. And do something else that's kind of funky. Let's do that right, unordered, yeah. This is actually going to be character to oh, how do you ready for this? Auto. to F, we'll call it, or I don't know, we call it op map. I don't know if I could actually do this. We could try. And it's going to be, oh, how do you do this? Make pair. Yeah, it works like this. It's kind of interesting. Let's make pair of like this operator, and it's lambda, which is int a, or long, it's going to be long a, long, oops, long b, return a times b. And do this a few times. A plus b, a minus b, and you say plus, minus. And I want to say the auto works here, but it's kind of funky. You can also do something like this. Declare type of something like this, standard unordered map of character to declare type of one of these functions. I think this also works. I don't know if you can do it this way. I think you can. But it gets kind of ugly if you do it that way. So you can just say auto. I think it works as well. I think I used a functional last time I did it. Hopefully that works. That op map. I don't know if can I just return. Oh wow, good spelling. See, this compiles. Compiler. Deduced conflicting types. Embed solution for initialize list empty type. Really? No kidding. Okay, what about this though? Unordered map and namespace standard. Did you? Oh. I thought I spelled that wrong. I looked at it a few times and didn't see it. Lambda expression in an unevaluated operand. Can I not do that? I can't find the declare type of this thing. Lambdas. Am I crazy? I did this before. I forgot how I did it. Can I do this? Auto. Not allowed in template argument? No? You sure? I guess we'll find out now. Unordered, or lambda as template argument. Lambda expressions, template class parameters. I've used this one. It's a very different question than this one. Stuff can be templated. Now outdated. Stateless lambdas, unevaluated context. Signatures, can of worms for mangling because lambdas are required to have unique types. Used to be, is indeed possible to achieve. Oh, nice. Something like declare type foo. Yeah, that's what I want to do. Restrictions are still in place. Can't appear on function signatures, but the described use case is not fully valid. The declaration of the variable is no longer necessary. You can't because lambda expressions shall not appear in an unevaluated context, such as declare type and size amongst others. Evaluation of a lambda expression results in a pure value temporary. Temporary is called the closure object. A lambda expression shall not appear in an unevaluated operand. We need to first create a specific lambda and then use declare type on that. Comp, whatever. Type def, declare type, comp, map type. Oh, that's exactly what I'm trying to do. Okay. Interesting. Each lambda-derived closure object could have a completely different type. They're like anonymous functions after all. Oh, interesting. Okay. You can use standard function, which is the type. Okay, we'll do that. That's how I did it last time, I believe. Yeah, I think I did it last time because you can use. I keep spelling that wrong, man. I don't know if it's function or functional. I think it's functional. Wow, I can spell like a freaking. Yeah. Yeah, lambdas can be, yeah, kind of interesting, but there's two ways to do this. You could write the lambda function, or you can actually write a function pointer signature, which is kind of interesting. But it would be like a pointer to a function. I think it's a lot easier to use the functional library, but yeah, you could actually do a pointer to a function here. I believe, but I prefer to do it this way. I think I prefer to do it this way. Not unction, and then it's going to be long. Oops. Long A, long, just long A, long B. How do you? Oh, that's how you describe a functional. Okay. Yeah, functionals are a little funky, and it's going to be a long way back home to see you. Expected unqualified ID. Excuse me? Oh. Okay, I don't know what's wrong here. I don't want to find out either. Let's see. Yeah, I remember this taking a while to sort out in C++. This is a lot easier to do in Python. Python kind of handles things a lot more loosely when it comes to the types. So if you want to do like a hash map of functions, and so you can associate an operator with a function, it seems to be a little bit less involved than in C++. But C++, you kind of need a bunch of different pieces. You could take a bunch of pieces to throw them together. You get your operation map. So now what I want to do is, why is this a problem? I should be able to have an inner class for, oh, that's why. Duh, that's my mistake. Yeah, of course, okay. Nice, so this, so far we're okay. Now what we want to do here with our parse is create these nodes as we go and add them to the Sentinel node. Didn't spell that right. Oh, I did. Okay. So previous, and we're gonna have an val. So we say if C is in this unordered set of operators, so we say ops.contain, or even not contain, just count. If count of C and ops, so it's an operator, then we set, so first thing we want to do is set val equal to 10 times val plus C as an integer. Interpret C as a long, increment val, so val is 0 initially. If it's an operator, then we're going to say create this node, previous. Now here's the thing, maybe I should just use a struct here. I'm so tempted to just use a struct. I think it's just easier. Set next, get next, all of that. Let's try it with a class first, see what it looks like. I think it's easier to use a struct. So previous, set next to this new node we're going to create now. My question is, once I run this parse routine, I think these nodes are not going to exist at all. Wait a minute, I gotta think about that for a minute now too. Because this parse routine is a subroutine, they're all going to be in local memory. Oh, that's super awkward. Well, you know, we can run the parse routine. We could inline the parse routine and just not run it as a subroutine. About that. That's kind of funny. Yeah, well, right. If we didn't want to run it as a subroutine, we could basically think about how we'd want to use our node class using dynamic memory. And we would then, we would think about how we would want to use our node class using dynamic memory, and then we would then want to using dynamic memory, and then we would want to Sorry, I'm just thinking. We would want to use dynamic memory, and then to allocate these nodes so that way they persist beyond the function call. And then we would also want to write a routine to delete the node, to deallocate the memory, deallocate the nodes. Yeah. Simplest thing to do is just create a recursive routine for the deletion operator and just check to see if the next pointer points to anything, and then just run the deletion on that destructor. So you would, yeah, you do it recursively, and then you would, if it points to something, run the routine, and then after that recursion occurs, then you would delete this node. So it would actually delete the nodes backwards, just delete them from memory, which is fine. I mean, we could do that. I don't necessarily want to do that. Yeah, I'm not going to do that actually, but that's sort of how you would handle the dynamic memory allocation. But we're not going to do that. We're actually just going to go ahead and inline this routine when it's done, which is pretty much just basically do this. Actually, I'm not going to do it when it's done. I'm just going to do it now. Okay, so input. This, by the way, doesn't get changed at all. Okay, that's good. Very good. Wow. Can we not? Okay. So yeah. So if this operation count, if it's an operator, this C value, then we're going to set this next to this new, we're going to create this new node, reference to that node, and we're going to use isOp is true, value is value, so we just do val, true, and no pointer. No pointer. Yes. And then we set previous equal to, oh, you know what we can do? Let's say node, new node equals this guy. And this is new node. And then previous gets updated to new node. And what's that next? Okay. Oh, my head. So I'm doing this wrong. Yeah, this is definitely wrong. So what you would do, excuse me. First things first, we're going to assume that the input is formatted correctly. So it's numbers and operators. So the first thing we see is going to be a number, and then it's going to be followed by an operator or the end of the string. And then it'll be followed by either, if it's not the end of the string, that'll be followed by a number and then another operator, and so on. So if we assume that format, then we can make this kind of simple, I think. So let's do that. Let's try that. So if C is an operator, or actually our new node is going to be whatever value currently is, not an operator, false. We'll create it's not pointing to anything. Yeah, new node. There's really two new nodes we're going to create. New node 1, or new node val, and new node operator. And we're going to say C val C as a long. This is true. And this can actually do it the other way around. We can create the operator, and then we can say this node is actually going to point to new node operator. Now, the thing I'm not sure about is, I don't know if I'm doing this right, because these local, I don't know if this makes any sense. I want to say that when I create these nodes locally, that because I created them within this scope, that they just disappear outside the scope. Something like that, something kind of crazy. Like I don't actually know if I can just point everything to these nodes and then they all survive. I actually have no idea. Anyway, new node operator and the new node val, which points to the operator. Previous set next node is going to be new node val, and this previous new node is going to be actually the new node op. It's going to be that one now. Yes. So once you find the operator, then you set the val back to 0 again. Otherwise, you're going to update the value. That character. Convert that character to. Now, what's interesting is you actually want to perform a conversion on this character. I forgot about that. Yeah. Yes. Whatever the value is you have here, right? So, and so when you see just a digit, you're just gonna increase the value by the digit. Once you see an operator, then you're gonna create a node for the operator and a node for the integer, and then you're going to node for the operator, node for the integer, and push those two nodes onto your linked list. And that's it. Super simple. Super simple. Once you have ended, there should be a value at the end here. And this Yeah, that's one more thing to do at the end. And what we want to do is check. I gotta sit down. What we want to do at the end is just check that our linked list exists or survived. For node h equals sentinel, did not spell that correct, sentinel header, and we say while h exists, update h equal to get next. Yeah, actually we do need to get next to it, don't we? I guess I should have just made this a struct. I'm not bothered with all this getters and setters. So we just want to print out each value. Okay, what does this do? What happens? Compile error. Okay. Unexpected. Where's that? H. 1, 2, 3. I guess we don't need that. Runtime error. No kidding. Okay, the runtime error is in here. Okay. What's wrong? Let's make sure we're not doing anything crazy here. Okay. Alright. Can't see it, but okay. So this is not really a problem, but this apparently is. So that causes a problem. Really? No kidding. Why? What? Why would that be a problem? That shouldn't matter at all. Just say final node val? I don't know. Might have something to do with how their compiler handles things. No, it's causing issues. Stack views after scope. What? Really? This is kind of what I was afraid of. Yeah, I think this is the problem. Yeah, I think this is the issue. I think it gets cleaned up. This this node, I think it gets cleaned up, and we can't use it anymore. May need to use some dynamic memory for this, which would be very annoying. Don't want to do that. I don't want to do that. Yeah. So if we actually just do this, and we say Sentinel get next. Sentinel, not that one. Dot get next, right? And then we say get val. Should have an error here, I think. Wait, what? Hopefully I didn't mistype that. Yeah, it gives us an error, right? I think before it actually just optimized it out so we didn't get the error, but right, that should give us an error. I didn't want to use dynamic memory. It's fine, it's not a big deal. It's what it is. It is what it is. Okay, so in that case, we're going to go back to creating a parse subroutine. Yeah, sometimes it's challenging to not do. Whoa. Wanting to do things the way you prefer to do them. Can't always do it that way. Okay. Back to what we were doing before. Also still bending over, which is wrong. I like Sentinel. Turn Sentinel. Yeah. I guess it's a good thing we didn't create, well, structs, it's fine. I have a destructor. So I was talking before about I was talking before about a recursive destructor There's no data to destroy. I mean, it's just a long and a bool. We could just leave those as is. We just need to next destructor, and then set next to null, and delete this. Something like that. I think that's the right way to do it. Yep. Call the destructor on the next node. Set it to a null pointer. So I don't have any hanging pointers. And or any floating pointers. I think they're called hanging pointers. I forget what they're called. Dangling pointers. No dangling pointers. And then delete what this is pointing to. Alright, we do that recursively. That should do the trick. Right, so these things exist. You know, we delete the next and then set it to null pointer and then delete this, right? Now we parse. We should have our node pointer. And now we can parse okay, what happens if we do this? What happens if we do this? Yeah. Really? Can't delete expression of type node. Why not? I guess that's a pointer now. Something tells me that's not right. 0, 2, 45, 1, 45, 1. Interesting. Oh. Right. You can use a lambda expression here, or a ternary operator. So you can say ops.count of hgetval and I can do well. As a character, right? That's, you know, that's true. Interpret as a character, otherwise interpret as a value. Probably should just do this. It's true, then we do character of v. It's not true, we just do v. How about that? Overload cannot be resolved. Oh. More time? Overloaded function could not be resolved. What? Oh. Okay. I guess the compiler isn't really able to resolve that, which is kind of interesting. Well, I don't does this work? Basically just an if statement. There we go. 2 minus 1 minus 1. Right. That's what we're after. This should just be an if statement though. If, you know, this thing, in my back, man, I don't know what I'm doing, why I'm doing this. If, else, yeah, okay. Right. Could try a few different test cases quickly with our parsing function here. Just a couple others. See if it breaks. 10, 0. Now that's interesting. 0 is not what we want to print. Invalid test case. Okay, nice. So we won't get the test case. Don't have to worry about that. Sweet. Alright. Back, man. So we don't want to think about this here. Excuse me. So as I was saying before, we are going to want to, we have a small parsing routine. It's pretty simple, character by character, and we assume the correct format. Pretty simple. Build our linked list, and now we want to write our depth first search on that linked list, where we're going to, the way that we're going to maintain the state is we're going to push the 3 nodes that we're going to remove onto we're going to create a new node. We're going to consider those 3 nodes, create a new node, take those 3 nodes out, put them onto a Sentinel node, attach them to a Sentinel node, and then obviously keep them pointing to each other. Obviously the tail node points to nothing, though. You remove it, and the head node prior to it obviously points to something else. And actually you're going to point that to what the tail node was pointing to, and what the head node was the previous head node. Those are now going to point to this new node that you create. And then you're going to maintain in the stack that head node and that tail node, what those are, and at the end, after you recurse, you're going to use those 2 values, that head node, the tail node, to swap those three nodes for that 1 node yet again. Swap those 3 nodes for that 1 node. Actually, you could just have a pointer to the nodes that you remove. You really don't need like a Sentinel node necessarily. I like having Sentinel nodes, but they're obviously not necessary. Okay, I kind of want to go like lay down. Excuse me. Excuse me. I really need to go to sleep now. I kind of want to finish this before I go to bed, though. Yeah, the hard part is definitely the depth first search. It's definitely going to be more involved than the other pieces. Shouldn't be too bad, but I don't want to do it. I want to keep stalling. That's okay. We'll go get it done. We'll do it. Also, my bending over like this is not particularly good either. It's definitely way better to be like squatting rather than hunched over, but I'm still hunched over anyway, even though I'm squatting. Not the best thing. Not the best thing. So yeah, I mean, I don't know. I could just throw my glasses on for the last part. Here. Okay, so yeah, even though I like getting some practice, using not using my glasses. But anyway, just throw this on so we're a little more comfortable. So we're gonna use the depth first search now. Okay, let's do that. And we're going to say, other way around. And we have a state that we're going to maintain. We actually don't really need much for the state. I think it'll actually be maintained for the most part. Pretty much it's just this T. Yeah. We have a ret we're going to use. Actually long of these values. So some base cases. If we actually do want a few things to use here. Node h get next. Just say generate case. Really, we should throw an exception. Yeah. Okay. Just say base cases. I made a mistake here, by the way. If the header get next is a null pointer, no. Okay, yeah, we'll do it this way. So get is up. Otherwise, red dot push back h get val. Not a value. Misformatted input. I don't really know. These are not going to be the most helpful. Whoa. Okay, anyway, not the most useful error messages. Okay, it doesn't look like it's spelled right, but it's 2 T's. Yeah, we'll just do both. This formatted input, yeah, both of these. Base cases, obviously return. I don't know if you throw. I don't think it's gonna. I don't know. I think we'll just throw return statements afterwards anyway. If you throw, I think it just stops execution there anyway. Okay. Now we have 4 node h, or just begin, or just pointer, we'll say pn. So the way we're going to operate is we actually we're gonna update n according to we're gonna, as long as n's not a null pointer, and we're going to return a certain pointer here. So this was a tricky thing. Okay. What do you return when you're done? Oh, this is interesting. Oh boy. I'm just thinking about this whole algorithm. It's like, oh, okay, there's kind of a lot of things involved. I don't know what we return here. I want to say you don't return anything. Just say you don't return anything. Leave it at that. I don't think actually you do need. I don't think you actually need to return anything. So what's going to happen is you got these three nodes. Say node pointers A, B, and C. A, B, C. A is going to be H. B is going to be H. Get next. C is going to be A. Get next. C is going to be B. Next. Now we would expect A to be a value. So we're going to say character op equals B, get val as a character if B get is op, if not throw new not an operand. Really it's or of these things. It's got to be, it's really three of these things. It's A, B, C. A is an operator, or C is an operator. Something like this. Not a value. So we're going to say long new val. It's going to be, so we say or ops.count of, so less than or equal to 0, or is equal to 0, ops.count of character b get value, or just op, yeah, ops.count of op. If the count is 0, let me say not an operator. And now we're going to go ahead and say, really you could do op map. You really don't need ops. You could do, anywhere you see op, you could do op map. Actually, that works too. So now we want to say op map of the operator. I can use this notation. And we want to operate on A and C. Say long eval equals this. And then you say node pointer new node equals new node of new val false null pointer. Now the thing is, we have node tail, or C tail, we'll call it C get next, and there's A head and C tail. And A head is see, that's the tricky thing. We actually want previous. That's what we want at each step, not the head. Let's have this, yeah, do it this way. Do it this way. Previous. So there's a previous value, then the next, this get next is going to be the head. And we actually want to do it this way. And a little confusing. A little confusing to do it this way. Previous get next. So base cases will say if not previous, runtime error. Set the head to the previous, save the head, and head get next. Right, now we can do the same. Okay. So base cases, so if this previous value doesn't exist, or no node, null node, null node pointer. You say the head is previous get next. If it exists and the thing coming after it's a null pointer, then you have base case, check if it's a value or not. Excuse me, if the head doesn't exist at all, null node pointer. Again, excuse me. I guess it's misformatted input. And set p to previous, so a equal to h. Yeah, so we would say P is previous, ABC, A is going to be P, get next, and we say, you know, if not A, same deal. No pointer. Kind of do this at each step, don't you? A, if not B, and then finally C, and if not C. Okay. Yeah. So. P is previous, and okay. A, B, C. A head is previous, or P, and C tail is C get next. Okay. So now what you want to do is create this new node. You're going to stitch the new node. Previous nodes A, B, and C were, so A head, set next is going to be new node, and new node set next is going to be to C tail, and C set next is going to be a null pointer. So C is no longer pointing to its tail. The A head is now pointing to this new node, and A, B, and C are, and P is the same though. That's the thing. So P, so we'll say A head is set to P, right? Saved A head here. We set the next to new node, and then we set the new node to point to the C tail, and now A head is no longer pointing to A, and now C is set next, right? Pretty interesting. Recurse. So we're going to F of some things. Recurse. Store. Stitch A, B, and C. Where new node is now. Delete new node. So now you go back and you say A head set next to A, C set next to C tail, and delete new node. Just gone. Gone. You wanna do this before you delete the new node though, because you don't want to delete. Yes, it's kind of important. You don't want to delete what's the new node is pointing to, the rest of it, which is really C tail. So now you set A head back to A next and C back to C tail. And then set the new node to point to nothing. And obviously A head's not pointing to the new node anymore. You can delete the new node. Yeah, that should be fine. This shouldn't matter. Oh, you just need to say if not next. Then, right, small mistake there. And that's kind of it. That's the whole thing. It's pretty straightforward, believe it or not. No, there's a little more. There's a little more. F, you would call on. You actually. Once you've replaced. Once you've replaced, so you actually would call F again on the head node. I think it's, yeah, this previous node here, really it's P. Call F on P. P is going to change, call F on P. And you update P now to past A, B, and C. Which is actually C-tail, which is kind of interesting. Yeah, update P to C-tail. And that's kind of it. That's kind of it. You recurse on P. I don't know if this is right. Thinking about this is kind of interesting. This is not right. No, it doesn't really make sense, does it? Stitch out these nodes, stitch in these this new node, and recurse. And then you do a stitching again and again. The problem, though, is there's sort of an index that you operate on. So you have some P that you operate on, but you're supposed to recurse over, like, in other words, you're supposed to call this recursive routine I guess for certain values of P. And you actually have, it's kind of interesting, you don't actually change this head node, I guess. There's something interesting here. So I want to say there's two values here. There's like a previous and then there's like a current previous, something like that. It's kind of interesting. I want to say there's like another index here that we can use that index in the form of a pointer. So basically the recursion you want to do is that there's a few different spots, a few different values of a particular index that you want to iterate on, you want to recurse on. And those spots are going to be they're going to represent the first operation that you perform and replace that with a new integer. But no matter where you do it, you're still going to recurse starting from the beginning, the first node, the head node, every time. So it is kind of interesting. So you set P equal to previous, we'll call it, which is really just the head. So it's kind of the sentinel node that sort of never changes. So that should never change, actually. So that should just always be previous, right? That's just always the same. However, there is this other value P that you operate on. And you would actually recurse. So the interesting thing is you don't actually need to provide P to F at all, I think, because P is going to update to C tail, right? It actually is not going to be C tail, it's going to be C. P should actually be C. That's like the new previous value, I guess. Yeah, A is going to be the thing that comes after C. And A head is what P is pointing to, right? Right. Yeah, because you remove these 3 nodes, put a new node in, recurse on the whole thing from left to right, the whole way. You made one substitution. Then when you put it back in, now you shift P over to another spot. It's actually going to be, believe it or not, it doesn't shift that far. It actually shifts to A operator B. It's A, B is the operator C. You actually want to point to the operator, which is B. P is actually going to point to B, which is kind of interesting. That's the previous value. The next, yeah, you're going to have the next 2. Now you're going to combine them and do a recursion, and then replace that, and then go to the next one. And so I think this is what it's supposed to look like. It's super funky, and I don't think you even need to. I don't think you even need to. I don't think you need to do very much more from here. I don't actually know. Parse input is create the sentinel node. Yeah. I think T is just, yeah. Okay, what happens? What happens if we do this? Compile error. Why is this wrong? This is a character. Compile error. Can we not do this? Hello? No matching function. Oh, gotcha. Understood. Yeah. Completely forgot those are nodes. Oh. They want integers, okay. Fair enough. Okay. I guess I don't need longs. Runtime error. Member calling no pointer type node. Nice. Of course. When does that happen? Let's see. Hello, hello. Okay. Just make sure we're not. When could I possibly be calling on a null? Oh, here previous is covered. H previous next. H is covered. H next. H is covered here. Right. It's. Equals previous, A, B, and C. Oh. Yeah. Equals B. Wait, where is this? Where is this happening? Actually, I thought I had all my bases covered here. I must have missed something then. Huh? What? Excuse me? Where is this? I actually can't find it just by inspecting it. I think if I inspect it a little bit longer, I'll find it, but somewhere in here is a... Okay, we don't make it that far, huh? Oh, is this when it happens? Really? Oh, yeah. Okay. What? Oh. I'm sorry. I made a mistake. Stack Overflow. Nice. What is going on? Excuse me? Oh. No, this is where the... Wait, what? What in the Sam Hill is going on? Oh, we can't do this, huh? Okay. Oh, I think, interesting. Alright. If this is a cycle, if it points back to itself, oh, that's interesting. B points to A, which points to, huh. Wait. But no, but it's not, doesn't point to anything. What? Huh? Nothing points to what? What is going on? Huh? Huh? Okay, this is very confusing. Oh. Right. What does this do again? I don't know. Confused. Need to use this more often. Excuse me. What does this do again? Okay. Okay, I think that's why we had Stack Overflows, because I think I understand. We don't need to, no, don't do that. If there is something here, and we want to operate on that, if next exists, delete next. I think that's what we want. That's what we want. Yeah. Okay. Tricky little thing here. Terminate call that's throwing instance of standard runtime error. Nice. One more time. can tell I do a whole lot of memory. Oh, it did work. Oh, okay, interesting. We didn't make it again though. P equals B and then some runtime error occurred. Okay. Just throw this in here. Definitely didn't make it down here. Don't think we made it to Y. X, Y, X, Y, X. And somewhere between X and Y we run into a problem. Let's see. I don't know. Just say A. B. And C. Ooh. Let's see what we get. B. So B is the problem. B is non-existent. A is P next. And B doesn't exist. Interesting. Right, that would make sense. You actually just terminate there. I was thinking about that before, and I was like, you know, I don't think this works the way I think it does. And I was somewhat correct in that this does terminate a little bit sooner than I thought. B's last operation consider. So we say B, get next, if not, or not B, get next, get next. So if you don't have B, or the thing after B doesn't exist, or the thing after, really this is the next operator here, then you would just break. Huh. Got the right answer. Okay, get rid of all these other things now. So this has been fun. It's been an interesting adventure here. With the Y's, where's that coming from? Yeah, there we go. Okay. Pretty interesting. Yeah, pretty interesting so far. Let's try some other test cases here. Just breaks everything. Everything just breaks. Wrong. Wrong, wrong, completely wrong. Don't be ridiculous, it's so wrong. Now, 10, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. Uh-huh. Oh, that's interesting. So, excuse me. What's wrong here exactly? What is the issue? Apparently, I need to have it in the same order that they have it, or can I just -10, -10? I got -14 twice. Is there a way to get -14 twice? Yeah. Oh, that's interesting. Oh. So you can do this and then this, or you can do this and then that. And it's considered the same formulation of parentheses. Oh no. Uh-oh. Uh-oh. Well, that's very interesting. Yeah. Huh. Oh no. You gotta be kidding me. Oh no. Oh no. Oh no. Okay. Uh-oh. Uh-oh. How do you sort that out? Excuse me. Oh no. There are a number of problems here. There are a number of issues here. So let's just test something here. Actually, my algorithm is wrong. My algorithm is wrong. Finally coded up right, but it's wrong. First things first, is there an order that matters? What did we say this answer was? 10, we just need to remove one -14, right? 10, -14. Alright, what if we do this? Alright, doesn't matter what the order is. Yeah, okay. So it does have to be just the right number of these things. But the question is, you could do this one first or this one first. And then just, in other words, you could do either of these and it won't affect, in any order. And this algorithm, the order matters. Which is interesting because How do you factor that in? The order doesn't matter in certain cases. You gotta be kidding me. Excuse me. Right. Right. Hmm. How the heck are you supposed to figure that one out? You do this one, and then you have a choice of two others. And you could do this one, they have a choice of two others. And huh. Oh wow. Whoa. Whoa. Excuse me. This is crazy, man. What? Oh no. Oh no. Oh no, I gotta go to bed. I'm gonna lay down for a minute. Oh no. So yeah, you could understand these things as like, I guess, operator trees, something like that. Oh man, you gotta be kidding me. No. What? Excuse me. Wow. Oh man. You've gotta be kidding me. Yeah, there's a tricky little thing here where sometimes the parentheses doesn't actually give you the full order, if that makes any sense. other words, if you have, oh, you gotta be kidding me, man. That's so much harder. I can't even articulate it. Oh. Wow. Because you have these parentheses from left to right. 2 times 3 and 4 times 5. And if you do 2 times 3 first, or if you do 4 times 5 first, you do the other one, and then the other, and then the 1. Not only do you get the same answer, but it's the same expression with parentheses. It gives you the same thing. There's no way to specify that you do the left one or the right one first with parentheses. Whereas the algorithm that I'm going through basically suggests that you can select which one of these expressions that you calculate first. Oh, that's super interesting. Wow. Huh. Excuse me. So maybe there shouldn't be a linked list that we use. Maybe it should actually be a tree structure. And we say, okay, you can make the head of the tree can be any of the operators from left to right, and then the left subtree is going to be whatever's to the left of the operator, and the right subtree is whatever's to the right of the operator, and then you recurse on all of those possibilities for what those trees could be. And so the middle operator, there's sort of the left subtrees that are possible and right subtrees that are possible. And what you would do is you would say for each left subtree, there is a possible right subtree, and each subtree gives you a value that you're interested in. So you would say for each, so there's a left subtree and there's a right subtree, and for each possible value of the left subtree, there is a possible value for the right subtree, and you take the cross product of those possibilities to give you the final results for a given tree, I guess. You take each of the values in the left subtree that results from the left subtree, and the possible results in the right subtree. You take the cross product and apply the head operator, and you do that recursively for each operator from left to right. I want to say you do it that way, and I want to say that works correctly. That's a much more apt. This idea of like using a binary tree is much more of like how it works with parentheses. Yes. The key difference is you get the count correctly. That you get, you don't double count. I'm so annoyed though. It doesn't need to be. Actually, you could recurse on linked lists still. It actually doesn't need to be. you could still parse this into a linked list and still operate as described. It's just, you got, the approach is different. Instead of using a depth first search, you use a divide and conquer algorithm, which I think shouldn't be too hard to code it up, but like, it's really funny. Yeah, it shouldn't be too bad either. Actually, divide and conquer. Actually, depends on how you do this. I'm thinking about it. I think a tree structure is kind of good. I don't know. I'm actually not sure how to do that. I think in theory that works if you had some magic algorithm or some black box algorithm that you sort of process the left side and process the right side of the operator and you get all the possible results and you take the cross product. And then each of those should be correct. Yeah, and then if you put that negation symbol in the middle, or the subtraction symbol, then on the left side, the only subtree you have is 4 times 5. And then on the right, or the left side is 2 times 3, and the right side is 4 times 5. And that's it. There's no, yeah, that gets rid of the ordering that we were looking at before, right? If it's, yeah, right, that removes any issues we have with orders, with order. Also, I'm hearing a noise that doesn't sound good. Sounds like something's pressured. A pipe or something, I don't know what that is. But anyway, yeah, so a kind of recursive algorithm should work, but the problem with that is, I guess you need like a range of, you need pointers. You need a range over pointers. So in a linked list, I guess that's fine. Yeah, I guess you could do a range of pointers in a linked list, and you basically would, at each operator, you'd sort of split the range of the linked list and operate recurse on one side and recurse on the other. And you do it recursively. So in theory, there's O of n operators, and so you recurse on O of n times. I mean, each recursion is going to reduce. Now this is kind of interesting. The runtime, I think, is quadratic. I don't know if it's quadratic. There are a lot of possibilities, I guess. You actually, I mean, you could still use a linked list. You don't really need to use a linked list. You could use as a kind of an array, and indices in the array. I'm just thinking. Yeah, that should be fine. That should be fine. Thinking if there's a way to. There's a few things to think about with this problem now. I don't know what the runtime is. I want to also say something about using dynamic programming as well. I want to say that it's exponential, but if you use dynamic programming, then it becomes quadratic. Something like that. Yeah. Pretty interesting. I definitely want to use an array and not use, we could use an array of tuples, use an array of pairs. Not really tuples, but just pairs. And I could tell you whether it's an integer or a number, or a character or a number that you're dealing with. Or rather, if it's an operator or a number, when you parse into an array. And yeah, like I said, operate on ranges of the array, but it's definitely, you can use dynamic programming to reduce the runtime. Certainly, I do think it becomes exponential if you don't use dynamic programming. Like if you do use like a 1,000, then you recurse 1,000 times, and each of those recursions, there's some symmetry, but let's just say from left to the middle, and then you just double that, right? The double number of calls, because right to the middle is sort of the symmetric calls. But left to the middle, now you have 500. You have 1 and 999, or how many actually operators do you have? So if you have 1,000 characters, or you have 2,000 characters, every other character should be an operator. So let's say 2001 characters, you'd have 1,000 of those would be operators, and another 1,000 would be numbers. 1,000 numbers, 1,000 characters, and then one more number at the end. Yeah, so it's n minus 1 over 2 operators. So roughly half of n. Yeah, so you'd recurse on half of n. That's how many times you would recurse, which is a lot. And then each time you recurse, it sort of depends, but you don't have a balanced tree that you're working on, I guess. You have one element, so you have one less character, so it's n over 2 elements in each array, right, because you remove the operator. And then you have one on the one on the left side, and then all the other 1,999 on the right side. It's always an even number that you're working with, or odd number rather. And then you're performing the similar recursion on, n minus 1 over 2 times for 1,999. Yeah, there's just a ton of recursion that goes on. It's really a lot. I think, I want to say actually the best case you can do is if you use dynamic programming and then you end up doing at most O of n squared work, right, where I and j are the indices that you're operating over, and you just save the results for each of these indices that you operate over. No kidding, really. Well, this is a really interesting question, I have to say, now that I'm thinking about it, looking at it. Wow. This is a very, very good question, very interesting question. But I think that's the way to do it. Forget the linked list. You don't need a linked list anymore. You just use an array. And then you have the indices I and j, and you sort of divide and conquer. It's not a divide and conquer. It's a dynamic programming where you would recurse. You split on each operator. You split your range, and you recurse over that range. And for each range, you split on all the operators in that range. And you save the results of each of those recursive calls to memoize over a map for I and j values, tuples, or pairs rather. And yeah, you use a map. We could use a map because I and j are integers. We'll keep them ordered. Wow. Yeah, and then really simple, you just say whatever numbers are possible. You take that cross product of possibilities and apply the operator on each of those pairs to give you the new return value. And then obviously the base case is super simple. The base case is just if you have a single number in that range, then you don't have any operators. Or if I is equal to j, really, then you just return that number. It's a list with just one number. Yeah, interestingly enough, this is a lot easier to code this solution, but wow, just wow. I can't believe I got it wrong though. That's so annoying. This took me a really long time to figure out. If I thought about this a little bit more sooner, I think I would have finished it a lot sooner as well. This whole thing is way more complicated. Excuse me. I still want to use this, but we don't need this anymore, obviously. Don't really need exceptions anymore either. Excuse me for what we're about to do. Yeah, none of this is really necessary anymore. We can do the parsing we still want to do. We want to have a vector of use tuples, why not? That's part of utility, I think, or just tuple, yeah. All right, We actually don't want an unordered map anymore. We just want a regular map. It's going to be a tuple of ints, and it's going to be a vector of ints. Call it memo. And we're going to have parse string node. It's not going to give us node, it's going to give us a standard vector of tuples, and they're going to be really good just pair. Yeah, utility. I need an int and boolean, so alright, so parsing, we get this int bool pair. We don't really need nodes anymore. We don't really need value, it could just be an int. We already know it's going to be ints. C map count. Let's just say int val. No, I mean you just need. Oh, actually, hold on. So a new node val. We're gonna new node. So the value is gonna be red.pushback. Standard make pair val false and C as an integer true. We don't need any of this anymore. Val equals 0. Otherwise, increase that value by a char, whatever the digit is, right? Convert it to an integer. And then you say the last value, ret.pushback, val false. And that's it. Okay. And now, what we're going to want to do is we parse into our array. And we'll say input, I don't know, we'll just call it array. Parse the input string. And now what we're going to want to do is if this memoized function auto recurse, it's going to look like the following. Which is have this array, which technically we don't need. Yeah, technically we don't really need these, but we're going to do it this way. We'll do it this way. We say base case if I is greater than j, turn, right, and this is obviously instance. One value, and the value is going to be array of I. And then otherwise, we say curse on each operator in the array. Right, if any of these things are true, then we're just out of bounds. Each operator in the array range. So for int x equals I plus 1, I is less than or equal to j, I plus equals 2, x, yeah, I is always going to be on a number, and j is, x is always going to be on an operator, and we say, so there's a few things, and then f at the end. We say two things. So we'll say left subtree, or left and right. I could say auto, or left, or right. But these are going to be just vectors of integers. And we say I to x minus 1 and x plus 1 to j. Right? So this is going to be, there's a range from I to j. There's a bunch of operators in between. Index I, index I plus 1 is the initial x. We know that's an operator. We don't even need these pairs, actually. That's not even necessary. It doesn't need to be a pair. It could just be integers. It really doesn't matter. Because we already know it's going to be an operator or not because of based on its position. Yeah. Oh yeah, this was wrong anyway. It was just needed to be a standard make pair. That doesn't matter. Yeah, it doesn't even matter. So, so anyway. So, we don't really need this either. This should be able to, I think it'll be able to deduce the return type. Okay, so I is like 0, x minus 1, right, x plus 1, so you don't include x, and yeah, you go to j for I, right, if X is less than or equal. It really should be just less than J. It'll never be equal to J. It should never be equal to J. But anyway, so you have left and right. Now, these cases, we say if memo of tuple ij dot count. It's going to memorize this, but it doesn't really matter. Each operator in the array range. And we would say for int a, or just really it's auto a and left, auto b and right. We're going to say just thinking. Yeah, that's fine. So you take this array of X, consider it like a character. That gives you an operation map, and then you can apply that operator to A and B, and push that back into your return vector. And then at the end, you have ret here, and you say memo of key is ret, return ret. Right, super simple. And you would say recurse of recurse parse recurse. You want to parse array memo you actually don't want, oops, you don't even really care about this part. Just have, or actually you kind of do want this. And that's really it. You just return that. Oops, no, not that. Yeah, just like that. Okay, how do we do? Compiler error. Gonna have to do type from initializer list. Okay. I guess that's fine. I don't know. I'm not really sure where to put that. Wrong, wrong, wrong. Nice. Sweet. Nice, very nice. Very nice. Wow. Wow. No kidding. Really? Really? Okay. Start with that. Start with the parsing if that works correctly. 245, 145. Okay, that's good. 10 in there. Okay. And we say we don't even get the 10 case correct. Really? Oh. Oh, there we go. Okay. That's better. Man, I could have solved this a while ago, huh? Could solve this really fast if I thought about it. I don't really need this anymore, do we? The parsing, yeah. That easy, huh? Let's try some other test cases. I don't know. 7 minus 2 times 4 plus 8 times 100 minus 20. 3 plus 4 plus 5 times 20 minus 1,000 plus 2 plus 3. I don't know, man. Whoa. Do we just go for it? I don't know. What could I even think of that could be? I don't know. I mean, if this isn't right, then I think we're in a tough spot. Let's go for it. Let's go. Oh, hey. Oh. I mean, okay. 0 milliseconds faster than all solutions. Wow. Cool baller. Cause I'm a boss, mate. Cause I'm a boss, mate. Cause I'm a boss, mate. No kidding. Wow. Wow. I mean, okay. I don't know. How long did that take? That took forever. Almost 4 hours we spent on this? Oh, that's horrible. This is supposed to be like a 15-minute question. Wow. Really? I need some more practice, huh? That I do. That I do. Yeah, I could have coded this up really fast. If I had seen this problem before, I probably would have coded it up faster. Oh, brother. This is taking me so much time. This is kind of non-standard. You know, this is like not your typical question. This is kind of unusual. Left and right subtrees. I mean, it's not, I don't know, it's a tree-based kind of thing. Not tree, but recursion, some dynamic programming, some recursion, memoization, a little bit of parsing. You know why it took me so long? It took me so long, and then there's, there's like other stuff here, finagling with functionals and, other things. But the reason this took me so long is because I had the wrong answer. I had the wrong answer, implemented linked lists, and then a manipulation that involved depth first search on linked lists, which was unnecessary. It was wrong and unnecessary and kind of complicated to begin with. I had thought of something like that it could be wrong because of this, of parentheses. If you sort of take a look at one side and look at the other side and the possibilities with regard to parentheses, the order, there's a certain, whether the order is sort of forced, sort of left to right always is the same. It's the same result given your parentheses, whereas what I was looking at was that basically you can permute each of those operations and get different results, which is not true. Pretty interesting. All right, sweet. So, all right, let's stop here. So thanks again for watching, everybody. I will talk to you all soon. Have a good rest of your day, rest of your Sunday. It's over here. There's not very much time left, but let me get going. Yeah, thanks again. I'll talk to you soon, and I'm not sure what else I want to do here. Basically just say goodbye. And yeah, say goodbye, say have a good night, talk to you soon. Just think if there's anything else I want to say or do here. I don't know. All right, I'll just go. Just thinking, I'm actually kind of like reviewing all the things that I did. Did a lot of stuff today. Today was an interesting, kind of an adventure. It's good. It was good to finagle with delete a little bit more. Yeah, because there's a deallocation routine and there's also the destructor routine, which are different. And when you call delete, it calls the deallocation. But anyway, I'm gonna go. Thank you all for watching. Talk to you soon. I already said that, but I'm just thinking if there's anything else I want to say for you. Not really. I guess I just go. I guess I just go. So yeah, take care. Talk to you soon.